We mentioned in the last video that Gaussian elimination is very procedural. It's perfect for technology to carry out. So in this video, we're just going to learn how to get a matrix into reduced row echelon form without having to be the computer ourselves. So we're going to use, and this can be done in graphing calculators, this can be done using any piece of technology. It might require a web search on how to do it with your specific device. However, I'm going to go ahead and use desmos.com/matrix to do this. So here we already have a system, a familiar system at that is in matrix form. So we can see that this will be something like 1x plus 1y equals 10, 2x plus 4y equals 34. And we don't necessarily know that the variables are called x and y, but we could call them x1 plus x2 equals 10, 2x1 plus 4x2 equals 34. It doesn't really matter what their names are, but the system that we're representing is the same. So what we want to do is to get this into reduced row echelon form so that we can read the solution. But before we go about that, let's think about what these two functions are. They're two lines in two dimensions. So x plus y equals 10 is this red line, 2x plus 4y equals 34 is this blue line, and we see that they intersect at the point 3, 7. So in other words, 3 plus 7 does equal 10, 2 times 3 is 6, 4 times 7 is 28, 6 plus 28 is indeed 34. So this is a point that both lines share in common. I'm going to go over to my calculator, and I'm going to enter this matrix in. So I'll press New Matrix. I want this matrix to have 2 rows for each of the 2 equations. I want it to have 3 columns because it needs to have the 2 columns for x and y, and then 1 column for the constants. So I'll enter 1, 1, 10, second row, 2, 4, 34. Now I'll just go ahead and press enter, or you can press the enter key here. Now we have a matrix defined. It's being referred to as matrix A. You can give it whatever name you'd like. And now what we want to do is we want to do the reduced row echelon form. So we have a button for that here. And then we need to tell it what the matrix is. You see that there's an error right now. It says function RREF requires an argument. The argument is just the name of the matrix. So that's the argument. And you don't even have to press enter. But if you do, it'll just jump to the next line. You see that that's the reduced row echelon form of that matrix, 1, 0, 3, 0, 1, 7. So I'll write down 1, 0, 3, 0, 1, 7. And now, keeping in mind that the first column represents the coefficients of x, second is the coefficients of y, and the third column are the constants. So we have that 1x plus 0y equals 3, or that x equals 3. Second row, 0x plus 1y equals 7, or y equals 7. So we now have our solution set in a matter of a couple of button pushes, and we have that x comma y is the solution 3, 7. Pretty easy to do with technology. The technology can carry out all the operations. We just need to understand what it is that we're giving it. Let's take a look at one more example. We haven't explored how to solve these 3x3 systems. Here we have 3 equations by 3 variables. Even though the matrix is going to have 3 rows and 4 columns, we only call the system by how many variables and how many equations it has. So it has 3 variables, x1, x2, x3, and then it has a column for constants. So what I'm going to need to do here, and you can call these x, y, z. Don't let the subscripts intimidate you. These subscripts are just another way of giving variables names. This system would have to be represented by 3 axes, so it's no longer a 2-dimensional problem. In other words, you would have to have an x-axis, a y-axis, and a z-axis. If you think about what that might look like, in 3 dimensions, the origin kind of represents the corner of a room, and these 3 axes are often labeled like this, x, y, and z. And so you can have points in 3-dimensional space by saying, this point right here is the point that is maybe 2 units in the x direction, then 4 units in the y direction, and maybe this is 5 units in the z direction. So this would be the point 2, 4, 5. Before we set this up, let's take a look at this representation. Many of us have maybe not dealt with 3-dimensional functions, but 3 lines in 3 dimensions are what we call planes. Think about like a plane, like land. A plane is really flat. And then where all the point, or points in some cases, we'll see later, that are shared in common by these 3 planes. So you can see the blue plane is x plus y plus z equals 10. The orange plane, which is actually this one here, is 2x plus y minus z equals 2. And then x minus y minus z equals 6 is this red plane here. So they intersect, they all intersect right there at that point that I just marked down. Let's solve it. Let's figure out what that point is. So we set it up exactly the same way. We just want to make sure that all like variables are in the first column, all like variables are in the second column, all like variables are in the third column, and that we have our constants listed forth. So we have 1x plus 1y plus 1z, or 1x1 plus 1x2 plus 1x3 equals 10. So 1, 1, 1, 10. Then we have 2, 1, negative 1, 2. Got to consider the sign. And then 1, negative 1, negative 1, negative 6. And it's just going to be as easy as, again, pressing that reduced row echelon form button once we have this entered in. So we might have to toggle back a couple of times here, but let's go ahead and do this. I'm just going to go ahead and we could create a new matrix. Let's create a new matrix. And we want this to have 3 rows for each of the 3 equations. It needs to have 3 columns for the 3 variables, 1 more column for the constants. So we have 1, 1, 1, 10. Then we have 2, 1, negative 1, 2. And finally, we have 1, negative 1, negative 1, negative 6. Okay, now this matrix is being automatically named as B, which is fine when we press the reduce row echelon form button. Or you could actually type in RREF, open parenthesis, capital B, close parenthesis, enter. And you see that there's the result. 1, 0, 0, 2, 0, 1, 0, 3, 0, 0, 1, 5. So we get 1, 0, 0, 2, 0, 1, 0, 3, 0, 0, 1, 5. Now, again, the order that we listed these variables in here, x1, x2, x3, and our constants suggest that 1x1 plus 0x2 plus 0x3 equals 2. We're reading it the same way even though it has 3 variables, which really, the first row says x1 equals 2. Notice that this reduced row echelon form, in contrast to the 2x2 system, it has 1 in the first column followed by zeros and then the constant. The second row has 0 followed by a 1 followed by a 0 followed by a constant, which really just says x2, 1x2 equals 3. And the third row has zeros in the x1 and x2 position, because we're only curious about x3, and x3 equals 5. So this point right here is suggesting that the intersection is 2 units along the x1 axis, or if you prefer, you can call that the x-axis, 3 units along the x2 axis, or along the y-axis, and then 5 units up, which would be the point 2, 3, 5. We can check our work. We can see that this still works out. 2 plus 3 plus 5 is equal to 10. 2 times 2 is 4, plus 3 is 7. 7 minus 5 is 2. 2 minus 3 is negative 1. Negative 1 minus 5 is negative 6. And so this checks out. So this is how we would, and we will go about solving systems now that we kind of understand how this works. By the way, if you were doing this manually, which we're not about to do, the same process would hold in terms of this Gaussian elimination. Get a 1 here, but now use this to get a 0 here, and then do another row operation to pivot off of this first row twice and use that to cancel out whatever coefficient we have in the third row. But then as we move inwards in the columns, our fourth step, should be a 3, our fourth step here will be to get this to become a 1. So scale the second row, use it to cancel out the value above and below it. And then our seventh operation would be to get this to become a 1, and then use that row to pivot off of to make this become a 0 and to make this become a 0. So you can see that that's going to require just more operations, 9 operations possibly in total if you don't already have a 1 pivot. You may be able to skip a step like here, you already have a 1. But doing this by hand is just unnecessary because the logistics are the same. It's just for a larger size system, which means more work for the human. And so this way we get to kind of take some of that work away from us and let the computer take control.